Good afternoon, everyone. Thank you so much for coming to attend this session. I definitely have to say it's an honor and a privilege to kind of come out here and talk to an audience of people and then streaming online afterwards. I think for me this is kind of a new venture in my role, and I'll just jump right into it. Who I am and what I do, just to kind of give you guys some brief introduction. So my name's Dan. Been in Autodesk for about 12 years now. Working on various products, starting back in the SGI days, working our way through Linux transition. Incinerator was one of my products way back in the day, which was a distributed computing, real-time grading render farm, basically. And today I find myself working on a group that's from our 3D division, from the Maya team, working more into what we're experiencing internally is a transition of how do we ourselves observe and basically adapt to the cloud. And I think that's the big question and the big decision a lot of our customers are going through, and even ourselves as well. How do we provide our services and software for the industry? And there's been many sessions already today, as well as yesterday, kind of touching on the cloud. Phil Peterson from our Shotgun team led a panel yesterday, a really great discussion. I highly encourage everyone to go and watch that online once it's posted. Later today, we'll hear from other studios as well and just their adoption of the cloud. And I think that's really the question that comes up here is, what does that mean to people? And fundamentally, this is really the stage of the industry. And so that's what we'll kind of go over. We'll go through what does the cloud mean? What's general usage patterns that we ourselves are seeing and what we see, our customers adopting to. What are those challenges and considerations? And I think that's fundamentally the big leap. How are you going to go about it? And really open source. And there's many different frameworks out there, and we're lucky to have some very special guests who I'll introduce a little later to come and talk to those points for their points of view, how they're contributing to the equation, and basically there's a lot of things to consider in that adoption pass. So fundamentally, we call this session the big decision, but if you're in this room or some of you may have already made that decision. You are moving to the cloud in some way, shape, or form. And then, what are those questions that remain? There's really the balance of complexity, cost, and capacity. This is really what do you need for a given job? What tools do you need? How are you going to go about it? What's your workflow? What are you trying to bring to the table and leverage with the cloud infrastructure in a given way? So we'll cover a bit of, what does that mean? How we as Autodesk are positioned and what we're thinking strategically on a high level that would help make that accessible, and who are what the partners and collaborators that we're working with to engage on that front. So this all starts where I like to call location, location, location. And I put this together actually a few months ago, and I already think it's outdated because this is such an evolving, fast-paced ecosystem for infrastructure that looking at just the three core public cloud providers, and never mind the private hybrid cloud providers, those are a big equation as well. I couldn't fit them all on the map, let's put it that way. So looking at the core guys, Amazon, Google, Microsoft, these are all strong players in the public cloud space for M&E. Looking at this, like what's the right one for you, where you're based, latencies and so on, your connection to the data center, and we look at this as a great opportunity for us to explore partnerships, looking at a great opportunity for us to enable an open ecosystem for our users and for our tools. And here, for example, are some of those use cases. So when you're looking at a pure cloud computing use case, what we like to call translation. It's the data in, data out, it's the heavy lifting, it's the data prep, to help you get through that content creation process for visual effects and animation. It could very well apply to many other industries as well, and you'll see a live design demo where we're showing cloud translation process from CAD data into real-time engines in our case. And this is where why would you leverage the cloud? What infrastructure do you need to help accomplish this heavy lifting that normally you would rely on local infrastructure? Or perhaps you don't have local infrastructure and you're quite literally relying on your workstations that you're turning into a render farm overnight, for example. So there's definitely a lot of common use cases that we're all exploring and trying to tackle in some way, shape, or form. So, for example, it is that hybrid ecosystem. Why were you bursting? You need scalable on-demand capacity. You've saturated local capacity. Your team is growing, for example. The pipeline is saturated in every single respect, what does that mean for you to actually move to that on-demand capacity? So looking at some of those use cases, we have the cloud service providers. These are the guys who are offering that end-to-end solution, rendering as a service, for example. These are Google's Inc., who we've collaborated with on a rendering service. There was a presentation yesterday from Todd with a great customer showcase, basically talking about what benefits did this bring for a studio that previously was just a bunch of guys working in a room, and they were growing their business, being able to manage cost and capacity in a very effective way. Meanwhile, the complexity is very much abstracted under the hood through the service, because the service itself is just offering a very dedicated and very direct line to take your data, translate it, render it, deliver results, meet your deadlines, fundamentally. And so this is a great model for people who don't need the complex pipeline. You're using general tools out of the box, and this is where ourselves as a company, we see a lot of opportunity to keep growing that and providing that service for that type of user. But then you look at what happens when you're in another tier. This is where, okay, the out-of-the-box solution worked great. Maybe your pipeline gets a little bit more complex. You have a more custom workflow for how you're generating your content. And this is what we call the DoItYourself Cloud. This is really about, it's a cloud platform. You may have heard the saying, it's just someone else's computer. I'm going to challenge that in some ways today. That's not necessarily the right way to look at it. But from a fundamental point of view, yes, there are additional computers that are going to be available to you at a given cost per hour, per minute, for example, but you need to bring your own tools. You need to bring your pipeline. You need to work with multiple vendors to help bring your ecosystem in some way, shape, or form to the cloud. And that's where I think this is where the complexity, not just from an infrastructure point of view comes in, but also for a data management point of view, and from a way that, how do you balance the equation between local and remote resources. I like to use this quote as a bit of inspiration for, this is a lot of conversations I've had from many users, and from, just what does that mean? When is a cloud not a cloud, right? This is ultimately the question we ask ourselves when we look at how do we deliver and adopt our software for an environment that isn't just a computer that's running 24/7 in your own server room. This is dynamic resources. This is how do you optimize so that you make sure that the type of resource you're using for a given job is the right one, so that you're not running cost overruns. This really comes down to, at the end of the day, are you getting the most efficiency out of your choice of infrastructure, and is your tool designed to run within that environment in the most optimal way possible? I think this is a way for software vendors such as ourselves to look at what is our portfolio of tools, how can we make them more aligned with fundamentally what I like to call modern IT practices. This isn't just about cloud computing and distribution computing, this is new ways to deploy and install and manage software that ultimately relies on a scalable infrastructure. So just to kind of put some paraphrasing around it, these are the do-it-yourself building blocks. This is where we say, okay, you're a studio, you're trying to make that transition. Okay, what do you ask yourselves? You have the production team coming up with concepts, you're coming up with stages, you have a budget. You have kind of business logic around how you're going to be managing the team, what kind of billing you want to be able to do when it comes to your customers, to the managing your own internal billing for the resources that you'll be using. Then you're starting to deploy okay, what type of user do I have? Admins, technical staff, production people. There's a whole slew of characters that need to be kind of factored into the equation, and how you're going to be enabling them to leverage these scalable resources. And that's where we go to, you have your pipeline, extensible frameworks. You need to bring your tools, you need to adapt to the new paradigm of local versus remote infrastructure. How do you balance and manage those resources from a scalable, turn them on when you need them, turn them off when they're done. You don't want to be paying extra time on resources that may be sitting idle, for instance. This is really the cost efficiencies that can be pretty scary when you get that monthly cell phone bill and you realize you've been roaming overseas for too long. And then this is where it comes down to what are the tools you need. The software stack, looking back at those use cases where I described what are you going to be doing to do the data management, the translation, the heavy lifting, the inputs and the outputs, the simulation software, pick your DCC, pick your pipeline, rendering applications. You may have seen from a lot of our presentations today, there's definitely an open ecosystem there that we need to worry about and play a part of, and really be about how can we efficiently deploy and manage those tools. And this is where we start getting into the open source frameworks and processes like managed through Docker. What does it mean to actually containerize and deploy and orchestrate an actual cloud ecosystem? And so this is where I find, as a software vendor, when you look at this whole stack, there's a lot of opportunity for us to make this more accessible, make it more fundamental, how we're positioning ourselves to offer these to customers, and really kind of keep the pick your platform approach, be as agnostic and open as possible, and really kind of embrace the idea that this is a very open ecosystem that in some ways the very guided workflows can really help certain use cases, but then in some cases you need to be a bit more tailored to an open idea and how you manage and drive the decisions that go on from the production level all the way down to the tools that are being used and resources that are being orchestrated. I just want to say, if anyone has any questions, by all means, please try and keep this interactive. We have a pretty good session time today, so don't want to bombard you guys with slides and PowerPoint. It's really great to hear some experiences that people have in the room with this challenge and what they've experienced. And it's really, I think that's the greatness of open source and the collaboration, how everyone is learning from each other. And if we had this conversation 5 years ago, it would have been a very different ecosystem than it is today. And I think 5 years from now, again, I look forward to the time where we're maybe not even calling it cloud anymore, and this is actually just about how you work and how can you make it efficient and to that effect. And really, it's not just, it's not something that's scary. It's really, this is how production will be done in the future. And I think that's really a great opportunity for us to kind of continue those conversations. And so to that effect, I'd like to welcome our guests, Eric Weaver and Joshua Colton. Eric represents the Entertainment Technology Center, the ETC, and yeah, Eric, please come on up and take it from here.
So I'm with the ETC, and what the ETC is a nonprofit think tank based out of USC. So what we focus on is change and how change affects production in the production world. So for example, some of the work that's come out of us include DCI and IMF, Interoperable Master Format, and the Digital Cinema Initiative. We were originally founded about 23 years ago as an idea George Lucas had, seeing a lot of change coming down the pipe. So what I focus on specifically is cloud and how cloud affects production. So about 3 years ago, we started this project, and the project encompassed originally 5 major initiatives to look at these areas and figure out how we can provide solutions around them. The first area was transport. How do you get to and from the cloud? The challenges regarding that. So we've got a lot of work that's rolling out on that kind of thing. Second was security. My team actually led the crafting of the current MPAA document. So we architected it and with the CSA and all the heads of security of the studios, and then handed it off to the MPAA, and they didn't finish it. Forgive us. Then metadata, we're doing a lot of amazing things in metadata, and then storage, long-term storage archive, and finally a common framework. And Josh Colton is the senior architect of the framework, which will be coming up speaking and giving you actually the real meat of the talk here today. Some of the other things that we do have open sessions to people to come to our quarterly meetings and other things. We also have a meetup around Docker and CoreOS and how it fits into the media lifecycle and how it affects production as well. We're also producing short films to test from the studios these technologies in place in actual productions, and stuff along that line as well. So at this point, I'm actually just going to go ahead and introduce Josh Colton. So if you want to come up, Josh. One other thing I do, though, is I run the NAB Cloud Track and VNAB, Virtual NAB Cloud Track. So online at YouTube, you can find, we produce about 30 to 40 talks a year online if you want to go and look at different things. So if you just Google VNAB ETC 2016, you'll be able to see some of those lectures that can be very helpful. Josh?
All right. Hey, so my name is Joshua Colton, and I'm going to talk to you about some of the actual practical solutions that we have to address the issues that we're seeing in the cloud, and go through and kind of talk about the framework we have, and also maybe have some questions. We could talk about any of the details here that you want to, because we've been doing work on this. I've been working in cloud for media production since basically since AWS started. So I've been kind of hammering at it for a while. So we ended up having a lot of problems that everybody's going through the same cycle of problems over and over again. And by getting involved with the ETC, we're taking some of those problems, digging into them, comparing notes with studios, with media production companies, and making sure that we're coming to kind of a common, what the common problems are, and finding solutions for those problems. So there, as Eric just said, he hosts the VNAB as well as the NAB Cloud Track Talks. But the VNAB talks are available on YouTube, so just search for VNAB 2016. These slides right now that I'm showing you are available online. I'll get to that at the end, in which case this link will work for you. I think it's probably hard to get work right now. So we all know why we're going to the cloud, right? I mean, it's awesome. Cloud equals awesome because of price and capacity and accessibility, right? You get your teams all over the world working. You get price that's, CapEx instead of, or OpEx instead of CapEx, so you don't have to pay for it up front. You don't have to put your facility at millions of dollars of risk before you get to go actually try and get any jobs. And unlimited capacity, right? But raise your hands if you've actually tested workflows in the cloud and or use the cloud in your production. Anybody? I'm going to say maybe 10%, okay? So probably that 10% of you say, the cloud sucks. And why does the cloud suck? Cloud not equal to awesome is, well, because it costs a lot, and scaling is hard to manage, and we've got security issues, and all this accessibility has implications, right? So the same things that are basically the good points are also the bad points. And actually turns out that we've done this all before in media production. We've had the cloud since the 90s. We used to call it, or maybe still call it, render service providers, right? And you'd take your assets, you'd ship them off to some render service provider, and they'd come back and, half your textures were black. And then you do it again, and it would be another 24-hour turnaround. So we know what the cloud looks like. We know what those problems are. We've been dealing with that in pipelines for a while now. And it really is the same problem, even though you may have control over some of the resources that in a render service provider model you did not have control over. You still have to engineer around those problems. So what we've come down to in terms of the framework is some core primitives that allow us to kind of work with these kind of problems, provide some solutions around them that we believe will make everybody's life a lot easier. So the first problem to consider is the cost problem. What is the cost problem? It's the storage, it's the egress moving the data out of mostly. You get the latency of moving the data into cloud, you get the cost of storing it, and you get the cost of taking your data back out of it. And you pay for uptime, which means that the less efficient that you are at spinning up compute and shutting it down again, the more non-valuable time you're spending with that instance in some intermediate state that's not actually doing any useful work for you. So how can we solve this kind of a problem? So what we identified pretty early on at my studio, and then again, this was reiterated by all the conversations at ETC, was the main areas, like a key point of complexity is being able to identify the data you're talking about, identify if you have it in the right location, if it's complete, if there's transmission errors. You want to be able to do that even if the file names are the same. So you might have something that's a new version, but saved in the same location. You want to be able to coordinate based on files because you might have render versions or work versions that are kind of stacking on top of each other, right? So you might have a version 2 that's right on the heels of a version 1, and maybe you can't run version 2 yet because if you did, it would clobber your files. Turns out you have this really interesting kind of single point of failure in just computing in general that everybody still has, and we feel like is an important thing to fix. And that key point of failure is that all of our tools that we use to transmit data are what you would call imperative as opposed to declarative. You don't say, I would like to have this file over in that location, make it so. You say, transfer this file right now. FTP does this, SCP does this, rsync does this. Think of it as like right-clicking on a link in a web browser. You're telling it to download it at that moment. A better way to approach this problem is to say, I would like these files to be in this location. Make it so whenever you can. And always try to make that true, right? Work indefinitely until that's true, right? We shouldn't personally have to be solving this problem of, well, the file transfer got interrupted halfway through, and now I have to deal with, whether it's a complete file or not. The file looks like it's there, but now I have to check the file sizes, check the hashes, all these other kinds of things. It's a user space problem. It should be automated. We know what the goal is. The goal is to make sure all these files are here, we have here are over there and correct. None of the tools really do that. So with the C4, I don't know if I actually went through these ID parts. So one of the main, the thing with identification is you can use naming conventions, but other organizations won't agree with you. You can still clobber files on top of each other because you have collisions between same file name and same location, but different files. So we want a system that everybody can use, that self-coordinates, that does not require some big centralized organization that you may or may not be able to connect to it all the time. You want to be able to deduplicate. You want to be able to optimize your network transmit. So you want to optimize storage and network transmission. So C4 IDs for the framework allow us to do that. It's a cryptographic hash of the actual assets, and it's encoded in a standardized format that's 90 characters long, starts with C4, doesn't have any dashes or special characters. So it has a very slight, it's basically for computers to use, but it has a very slight human usability element, which is that it's all, alphanumeric characters. You can double-click on it, and you'll select the whole thing. And you can take this, you can use it as a file name, you can use it in a database, you can use it in your software, and so forth. But it is absolutely immutable, meaning that a file, regardless of what name it is, that I have, if you have the same file, whether we ever communicated before, we will identify that file the same way, right? So if we see that this file with this ID is in the cloud already, we don't have to copy it to the cloud. And aside from that initial huge benefit of just being able to know remotely without doing file comparisons and so forth in advance, unlike tools like rsync that do these hashes as they go, this is stuff you would have pre-prepared. You are able to coordinate with different organizations and different software tools all over the world. So the next problem is when you're actually moving into the cloud is you're trying to scale that infrastructure. You want to take advantage of the fact that it's scalable. But then what happens when you have 500 machines hitting one NFS server with all of your data? Suddenly, the engineering that you applied to your data center in-house doesn't apply to the cloud anymore because you've got, you can spin up 1 million CPUs, but they're going to saturate your bandwidth on whatever storage allocation you've created. So now you've got to architect around that. With tools like the ID system, it allows you to synchronize all the nodes with the proper data in a way that's propagates the data, and then they can just be relying on their local data to do this. It just simplifies the whole problem of coordinating all of this data and moving it around. Queue management is also simpler because you have a very deterministic result. You know that if I start with this thing and I do this compute on it with this ID for the source and this ID for the compute, then I will always get the same result. And so if this machine does it, I don't have to check what it did. I can get agreement across a very complicated dependency graph of render queues, and you can get it to you can architect these things a lot easier using these tools. And the other problem is just the architectural complexity, like I was saying, where you just, now not only do you have to spin up virtual machines, but then you have to spin up, figure out how you're going to lay out your storage and how you're going to decide when to spin them down. Is it based on, CPU usage? Is on Unix? Is it like uptime? How do you know that the render isn't still processing and just, bound by the I/O time and so forth? So this is the kind of situation that we want to model and we want to be able to get around easily, which is you've got data in lots of different locations, lots of different organizations. You want to have an ID system and a workflow system that is interchangeable between all of these, that works without the participation of some of them, that doesn't get confused if you transfer some of your files via a messenger on hard drive to editorial versus a transfer online, that is discoverable so that if you just find some files somewhere, that you can have a mechanism of working out what they might be related to. So we want a universal workflow. So the universal workflow, the way I like to think about this for anybody who's familiar with node-based compositing is it's basically the same thing as node-based compositor. Right? You have a dependency graph that says, here I'm reading this data in, I'm modifying this data in some way, I'm combining it with other data, and I'm outputting it. The only difference in the framework model of this is that those nodes can be anything. They could be transfer my files to a different computer or tar them or do other types of Unixy type or just general computational tasks, do transcodes and do CG renders or whatever. They could be command line arguments, but the point is that they depend on each other. You do this thing, then you do the next thing. You do the, first you take all your files and you tar them, and then you transfer them, and then you untar them, and then you pipe them through the renderer, and then you put them into the compositor and you transcode them and so forth. And you want to be able to describe easily, you want to be able to describe a dependency graph that goes as far up the chain as possible, because the more you can do in one location, the more you can just take your data, put it in the cloud, do everything you need to do until you're done, and then just get the results back, the better. We also, because of the ID system, the fact that the IDs are discoverable, and the fact that you can create this immutable dependency graph, meaning that once I have the inputs and the computational tasks that I need to do, I know that the results will always be the same if I run them. Just like a compositor on frame 2, of that particular version of the composite, every single time you run that, if you don't change any parameters or any of the inputs, you should always see the same output, right? And so we're taking advantage of this. Other areas of computer industry can't really take advantage of this because they have machines, they have web services, they have things that change, that need to have an engine that's operating and changing. Media production has this ability to just look at the actual, when you do a version of a shot or something, that version is it. You're done. It'll stay that way forever. The only time it's changed is when you do another version. That's a completely new entity, right? So this model treats each thing as a fixed in stone in history, like a version and a revision control system that you could theoretically always get back to if you retain the assets. And this idea of indelible metadata, where once you have an ID that can't be taken away from the data itself, if you take that ID and you associate it with other data outside of the file, things like metadata, like, for example, in a file that has other pieces of information in it like this, and you put the C4 ID as an ID, you say, okay, this information is related to that asset that has that C4 ID. Now I can take the C4 ID of this file, and when I look this file up, I will always find this information, right? They're inseparable. If somebody were to change, for example, the ID, say, oh no, I'm putting this with a different file, or somebody moved the data around, I won't get confused. Either I have this file and it checks out to the C4 ID I have, or it doesn't. So you get this ability to bind, which we haven't ever had as a system before. You get this ability to bind your metadata with your assets directly. Somebody back there raising a hand? Yes, it is the contents of the file. It doesn't include file system metadata, things like mod time, file name, path, things like that. Right, but this could be a file, and I could put this in a text file. This is, I think, YAML format, so we could say whatever this is .yaml, and I could take this ID of that. So now I have an ID of a file inside of which there's another ID, and so I can follow that chain and also once I look up this file, like if I have an object store and I use my C4 ID as an object key, as a key to the object store, and when I look up the object store and I get this information, I will never get any other information, right? If I did, I would check it against my ID and I would say, oh, it's not the same information, right? So we've never been able to do that before, really. We've never been able to bind metadata to the rest of the data without embedding it in some way. And this, not only is it indelible, it can't be separated from the asset, but also it's, I lost my train of thought. Well, anyway, you can validate it. Oh, it's discoverable is what I was going to say. If you found this if you have an ID, you can search through all the files you have, and you'll discover this, and you'll be able to validate the ID. Yeah. Oh, okay.
Why are they not? Oh, there we are. Why? It seems like the YAML file is not coupled with any individual file, or with the particular file that's associated with. A YAML file is just a file that could be deleted, misplaced, moved around. Why not embed the metadata and the hash? Well, I guess that it's not important, but in the header of the file, for example.
Well,
because the use case here is
not all
that
file
I've got an
formats
EXR
support
file. I've got an EXR file, and we all know that in the past, like a Windows user might accidentally drag a directory into another directory, and you have no idea where this image sequence came from or something. But if you open up a particular EXR or query the metadata for it, you should know what project it belongs to, who wrote it, what machine generated it, and what associated metadata there
right,
is.
but okay, then the problem is you can go one way. You can say I have this element, and it has this metadata to it, and I have this metadata, and I guess that's a better way to say it. I have this metadata, and it's associated with this element. So this element is on this show, and whatever. But what if it's a flame element, right, and it gets used on 10 shows, right? This system allows you to say, well, I can have a database entry that says, here's for this show's use of that element, the metadata that's relevant, and here is another shoe that points to the same exact key, right, but different metadata. You can do that all day long, right? And what you couldn't do before is you could say, well, that's related to this file in /asset/ whatever in an actual file.exr, right? But if that gets moved or you can't find it, you can never find it again, right? It's like if that's not where it's supposed to be or what it's supposed to be, there's no real recoverability other than finding more data to support where it went.
Right.
But this says, hey, you may not know, you may have dug this up from an archive, you find this file, you do run C4 IDs on the rest of the file system, you'll find this other file, right? Even if you don't have a database that has them.
You're going to sleep. What's the search time for, bringing an archive online and running a C4 ID search?
Well, you do have to read through the data, but typically if you're going to pull that off of a drive, you're reading through it in the process.
Yeah.
So to run IDs as opposed to use assigned IDs are infinitely fast because they're instant. You do have to read through all the data to get the C4 ID. So it will take time. And if you're doing everything in your all the data that you have, then it will take as long as it takes you to read all your data. What we're doing, however, is promoting this as a universal standard so that it's getting computed automatically for you at different places, like during copy commands, during network transfers. You know, cameras will be generating them off of the camera, and software will be generating when you're rendering files out, so forth. So you don't always have to pay the whole, you know, rehash cost.
Last question.
Yeah.
Are you proposing that the IDs reside in a key value database that's instantly
We're not making a
accessible?
specific proposal. We're just making it flexible so that you can do that. The other thing is that people don't quite always catch on to is the fact that if you have the file, you have the C4 ID. The only reason you need to store the C4 ID is if you want to associate that file with something else, right? But if you have the file, you can get the ID at any moment. Just run the C4 ID on it, and it will be correct.
Thanks.
Another point of that is these processing tasks where you want to say, okay, this is good for an archive example, where you say, I have an input, this is the ID of that input. I don't care how it gets renamed, I don't care, you know, what file path it's put at in a remote computer. I want to make sure that this exact file is what, in this case, gets rendered. So this scene file is the one I want. It may be called input.mb or whatever, which obviously could be easily confused with any number of files. But what I am saying is it's specifically this C4 ID file. If you find this C4 ID, that's the one it goes with this render. If you don't have it, you can't do this render. And on the execution side, you could do the same thing. You say, well, this is this exact command line argument, or this is this exact executable, right? Which gives you the ability to create these deterministic processes, especially if, you know, if the tool that's doing the processing supports it. And so now you can say, okay, well, on one machine, in this case, for example, I could say, well, this is a really fast render. So you could say, well, is it better for me to transfer 12 megabytes per frame of a file across the wire? Or could I just rerun this process in a different location, and that would have the effect of transferring the data, right? Because I can compute in location. So you get to have choices like that, and you get to be able, and from an archive point of view, you can store the process, like a VM or a Docker container or something like that, the inputs, and you can rerun and generate the outputs and validate the outputs at any time in the future. So you get this ability to reconstruct this. The last piece is the security issues. So from a framework point of view, the problems that we're seeing here are that we need access control. We need to be able to say who can see this. We want to make sure that's declarative, because otherwise, if we say, you can't see this, here you go, right? Then it's like basically we're just trusting you won't look at it, right? But a better, of course, that's not a very provable process. It's blind trust, right? And not only that, especially the way the infrastructure is set up with all these services everywhere right now, is you're blindly trusting every different web service and service provider that you ever work with, because you're creating new account credentials for each of them, and it's not, you're just handing over control. If you're not doing anything else to ensure your security, you're just basically saying, I trust you. MPAA, for example, has certification. There's mechanisms by which you validate this. But all of these are kind of flawed because they have this fundamental flaw that you basically just at some point say, well, I just have to trust you. So we believe in a stronger security model that can be supported by strong cryptography. You have your assets that are encrypted at rest, which means that they are not accessible by anyone except people who have keys to access the file. So you can say, here is my file, don't look at it, and they can't look at it because it's encrypted unless you, at some later point in time, hand them the key. So we have a proposal that is in the works for this that allows us to do basically what you do with your web browser, where when you go to a web browser, it validates, hey, this is really Citibank. But it goes both directions, right? So I validate that this is really Citibank. Citibank validates this is really me, and whatever access controls that grants me is what we share. I don't have to share my password. They don't know it. Nobody employee there could ever derive or sign anything from me or log in on their own as me into their system. And the idea that makes this really compelling from a cloud and interoperability point of view is I would be able to do something like this. I could have a studio sign a certificate for one facility and a service, a web service or a rendering service or whatever. Then without just looking at those certificates like a web browser, I would be able to be an employee at the visual effects facility, prove that I have access to this movie, not by logging into this service, this web service, but rather by sending a signed instructions. So the API itself, every time I send a command across the wire as an API, it's encrypted to this entity, and it's signed by me, and my cert is signed by my visual effects facility, and the studio has signed the visual effects facility. And so even if we were disconnected from the internet, as long as we had all our certs in place, we could actually validate to each other without ever having validated with each other before. Which means that I don't have to log in, right? Any service could do this. I could be sending commands to services. Services, oh, are you really on this movie? Do you really have permission to use our infrastructure so that we can build a studio? Yes, you do. Great. No, you don't. If you don't, they can't even, in certain scenarios, they can't even decrypt what you've sent. All right. Hey. Okay, so, and one more thing. It's all open source. It's, the reference implementation is in, oops, I think I'm moving the cord. The reference implementation is in Go, but we're going to have it in all languages that are popular, like C and Python and so forth. You can find it at GitHub etcenter C4. You can, here's some of the features of the tools. Some of these are not yet released yet, but this is all coming out, coming out right now. Right now you can download the command line executables. You can identify individual files. You can identify folders with a single ID for all the files that are contained within the folder. You can do very high performance remote synchronization through a trick called Merkle trees that is higher performance than rsync, which is, I think, one of the most common ways to synchronize now. Has a dependency graph language so that you can describe graphs like a compositing node graph that allows you to kind of describe how you want a workflow to work, a pipeline to work. Threaded multi-target copy, key value store. So you can say this key belongs to this C4 ID, look up a key, get a C4 ID back, vice versa. A daemon mode so that you can have like basically a file transfer system, the PKI infrastructure in these languages. All the most common ones first, but right now for performance, because Go is compiled system language and easily parallelizable, that's what we started with. So you get high performance. So this is where you can get more information. You can email me. You can go to GitHub or come to the meetup or check out ccc.io. So questions or issues that you guys have that we could talk about how this might fix? Yeah. I'd like to hear more about the rsync. Okay. All right, so there's this trick. Once you have hashes of files, and this is all happening kind of ahead of time, so you have these handy, is let's say I have two files. I can take those two files, get the IDs of those two files, and I take the ID of those IDs. So now I have one ID represents two files, right? So now on one side of the network, I say, hey, what ID do you have for these files? And it says, I have ID whatever, 5. And so I say, mine's 6, you're not in sync. Give me the left ID. Oh, give me the right ID. Find out which of the two are not correct, or both, and send just those. Every time you step down this tree, if you can make a decision and say only one side of this tree has changed, then you can eliminate half of the files from consideration. So this is pretty commonly used in high performance, big industry types of tools, but it's not common to find in things like command line, rsync, and stuff like that. I can find, with just a few steps down this binary tree of hashes, I can find out of petabytes of data just handfuls, bytes of data that's changed and transfer only those bytes across the wire. So that creates a huge performance over any other system, including rsync. And you're verifying in the process that you're absolutely correct. You're absolutely in sync with the remote thing. It also goes to a little security trick too. One of the studio execs asked us how we could validate archive, right? They want to be able, if they're going to hand digital archive off to, say, Amazon Glacier or something like that, or just a service provider that has archive, they want to be able to perform as a legal procedure at some point in the future a proof of life, right? Like, prove to me that you have my data and you can recover it and you could send it to me if I asked for it. So what you can do is add a random number, send them a random number, and that you've pre-computed when you were doing the backup, but you store it away, and tell them, put this number at the beginning of all the files as you're hashing it, right? You're generating the C4 ID, put this number at the beginning of the file first, as if it was the header of the data. Do that for all the files, and when you get back, you'll get an ID. If they truly have all the files, you'll get the same ID. If something is wrong, then you won't. And just like the Merkle tree trick, you can kind of follow this binary tree down to find out where that disagreement happens. And they could restore a second backup or whatever, depends on their durability model. There isn't an inherent, this is actually not any inherent hierarchy. So normally you would approach this as, I have a whole bunch of files that I only recognize by their C4 ID. So it's just a big flat list of IDs and the data that that represents. So, in a file system, for example, you might use symbolic linking to point, right, the real file to that C4 ID. That automatically kind of deduplicates for you as you're doing that. Because anytime you write to a file, the C4 ID already exists, you're done. So, yeah, so it would work for flat files. And when you're doing file system type stuff, then you have to actually capture kind of separately the structure and the metadata, the file system metadata, like block storage devices have. Yes, sir.
What's the collision potential for your hashing algorithm?
I will buy you a car if it collides. It will not collide. The C4 ID is based on a SHA-512 hash. SHA-5, so we think there's about, what, 2 to the 268 atoms in the universe, and this will identify 2 to the 256 of them. It is astronomically unlikely that there will ever be a collision. You're more likely to find a random frame of a movie by randomly, throwing pixels into different colors for a whole screen. Yeah, it's extremely unlikely. So basically, we're just assuming it's not going to happen because it's just too big of a number. It's several orders of magnitude bigger than, say, a Google, for example. Any other questions? Okay.
Can I get the last one? So yeah, this is really interesting. So one of the failure modes in a system like this is that you can be tricked to think that something is a hash, but then the contents are actually different. So do you do any sort of validation where you say like, hey, here's the hash that I want to upload, and then they say, oh, I don't have that hash, send me the data, and then you send them completely different data that it doesn't actually match the hash. So you also have to have like a server-side validation component.
Yeah,
to
I mean, that's already network communications use MD5s and other SHA-1s and stuff as hashing on both sides to validate that we correctly sent the data, usually at a very low level, like at the TCP layer. And this supports that model because now you would have both sides. They would do that hashing, but it would be the SHA-512 instead. And SHA-512 is one of the highest performance algorithms on 64-bit hardware, so it's actually a good algorithm to use for exactly that purpose. And yeah, from a security point of view and all those reasons, you would definitely, as you're reading the data in and writing it to your storage, you would want to run the ID on the fly as you go, yeah. All right, so thanks.